Students, in chemistry, we study atoms, which are extremely small, or molecules, which, even if they're clusters of several atoms, are still extremely small. And yet we live in a world where we're human beings and we have hands and eyeballs, and we need to work with those really small substances in the lab on a scale that we can deal with. To make that work, we need to use huge amounts of those tiny, tiny objects. To make that possible, we use a concept called the mole. Now, to get that going, I'd like you to think about this. Let's say I'm going to a candy store and I'm buying trail mix in bulk. The way to do that is not to count up the number of individual pieces of trail mix, every nut or every M&M or every raisin. That would be totally impractical. Instead, at a store, they have you bag up what you want, and then you put it on a scale at the cash register at the front, and you pay by pound. Chemists do the same thing. Instead of having a price per pound for a type of trail mix, we have a number of grams per mole for different elements on the periodic table. So take, for instance, copper. Its average atomic mass is 63.546. Typically, we would round that to the 10th place, so 63.5 grams for every mole of copper. For iron, it's a little different, 55.8 grams per mole. For magnesium, 24.3 grams per mole. For chlorine, 35.5, it would round to, grams per mole. We would look up on the periodic table the element that we're concerned with, or the element we're going to work with in a given lab. Let's say it's copper, and find its average atomic mass in atomic mass units, 63.5. There's a certain number of copper atoms that weighs 63.5. For iron, the same number weighs 55.8. For magnesium, that same number weighs 24.3. And for chlorine, the same number weighs 35.5. There's a numerical constancy here. And that number was estimated by an Italian scientist named Amedeo Avogadro that allows us to translate really, really small atoms in atomic mass units to larger observable masses in grams. The number that he estimated is extremely large because the atom is extremely small. Here's Amedeo Avogadro. The number of atoms for which an element's atomic weight from the periodic table is also its weight in grams. It's known as Avogadro's number. And it's this number, 602 hexillion, which is insanely big, the number is. If you were to write this in scientific notation, which is much more often the way that we would write it, because there's so many zeros to write here, it would be about 6.02 times 10 to the positive 23rd. It's that number of atoms that allows us to translate an element from the periodic table onto a scale that we can actually measure out in lab. It's reasonable to weigh out 63.5 grams of copper and actually be able to handle it and look at it. And for iron, 55.8. But if you go much, much, much smaller, we just don't have the equipment or the ability to handle substances like that. Avogadro's number is so important to chemists that we give it a special name, the mole, and it kind of has a lame abbreviation. You just chop off the E, and the abbreviation is MOL. I don't know why. A mole is a unit that could apply to anything, much in the same way that the word that represents a number for 12, bet you know that one, it's a dozen. A dozen could apply to anything. Like, I could have a dozen pencils, that would be 12 pencils. I could have a dozen sheets of paper, that would be 12 sheets of paper. I could have a dozen atoms of magnesium, although that number of atoms of magnesium would be way smaller than what I could handle in lab, but I could still have that. The word ream is what we typically measure the number of sheets of paper in. So like when you go to the store and say, I need some printing paper, they would say, okay, here's a ream. How many reams do you want? It would be in units of 500. In the case of atoms or molecules, the unit that we use isn't a dozen or a ream, it's a mole. And you could have a mole of pencils. It would be an enormously large number of pencils. It would be a number of pencils that doesn't even exist. Like if you were to add up all of the pencils in the whole world, it would not equal 1 mole of pencils. If you were to add up all of the sheets of paper in all of the filing cabinets throughout the world, you might approach a mole. I think that's a reasonable amount of paper for the whole world. All of these filing cabinets throughout the world might have a mole of sheets of paper in them. A mole of magnesium, that's a piece of cake. That's just 24 grams of magnesium. I can go grab that from the chemical prep room right now. Okay, let's work on translating this. If you find sodium on your periodic table, you would see that its average atomic mass is roughly 23. So in a sample of sodium that weighs 23 grams, you would know that you have 1 mole if it's a 23-gram piece sample. What if you have a sample of sodium that weighs not 23 grams, but twice that, 46? Then how many moles do you have? Well, 2 moles. It's for every 23 grams, you have 1 mole. What if we have 69? That's 3 times 23. How many moles would you have? Well, it would stand to reason you'd have 3 moles. Okay, but you're not always going to have exact whole numbers of moles of sodium in your sample. Maybe you have a sample of sodium that weighs 52.5. Now, you can see from above, if 2 moles is 46 grams and 3 moles is 69 grams, 52.5 ought to be somewhere between 2 and 3, probably closer to 2. Turns out it's 2.28 moles of sodium. How did we get that? That's going to involve some calculation, and that's going to be a big part of what we're going to do in Unit 5 is how do we translate grams into moles? You end up, the short answer is you're going to divide the number of grams in a given sample by the number of grams per mole that is the molar mass of that substance. Molar mass. What do you mean by that? A molar mass is the mass of 1 mole of any substance. It could be a lone element. It could also be a compound combined, which consists of several elements combined together, stated as a number of grams per mole. Molar masses can apply to individual atoms or compounds. If we consider the molar mass of just plain carbon atoms, you would look up on the periodic table the average atomic weight of carbon, and you'd find, if you round to the 10th place, 12.0. 12.0 grams of carbon is equivalent to 1 mole of carbon. How about just plain hydrogen? Find hydrogen on the periodic table, look at its average atomic mass, round it to the 10th place, and you would get 1.0 grams for every mole. But what if we have a compound that consists of 1 carbon and 4 hydrogen atoms, CH4? We can find the molar mass of that compound simply by adding together the number of atoms of each type that you have in the formula. So if there's 1 carbon, well, I'd add 12. And if there's 4 hydrogens, I'd add 4 times 1. That means 4 altogether, would give me 16 grams per mole for the CH4 compound. Ooh, okay. Now we've got this gets a little more complicated, right? Because we can get potentially large compounds. Let's do a pretty tough one together. Let's walk through this. What if we have a compound with many atoms in it, like ammonium phosphate? What would be ammonium phosphate's molar mass? Okay, we need to know something about nomenclature. I remember binary ionic nomenclature. I remember polyatomic ionic nomenclature. I even recognize the name ammonium. I think it's on my list of polyatomic ions. I might look that up. I know that because the ending is ate, phosphate is also a polyatomic ion. So I need to refer to my list of polyatomic ions or memory and devise the formulas for those two ions. If we put those together into a neutral ionic compound, notice that ammonium's charge is a 1 plus and phosphate's is a 3 minus. So to write a good formula for a neutral compound, we need 3 ammonium ions for every 1 phosphate. Please don't confuse the subscript 4 at the end of the formula for having 4 phosphates. There's only 1 phosphate in that formula. The subscript outside the parentheses is what tells you that there are 3 ammoniums. Now, if we apply that formula and try to give an accounting of each type of atom that appears in that formula, we would say, okay, we have altogether 3 ammonium ions, each of which contain 1 nitrogen and 4 hydrogens. So we've got 3 nitrogen atoms. We have 4 times 3, or 12, hydrogen atoms. There's 1 phosphorus and there's 4 oxygen atoms, all in that compound. Next, look up on the periodic table each of those elements. Look at the atomic mass or atomic weight. Round that to the 10th place because we're going to need those numbers. So look up and find nitrogen. It's element 7. Find hydrogen, element 1. Find phosphorus, element 15. Find oxygen, element 16. I'm sorry, element 8 with an atomic weight of 16. And I like to round to the 10th place because it's accurate enough and it doesn't get us bogged down with too many decimal places. Now, we've got that taken care of. We're going to do a little bit of adding. We're going to multiply the number of atoms within the formula by each atom's atomic weight. So for nitrogen, there are 3 atoms, and each atom has a weight of 14.0. That gives us, if you multiply across, 42.0. Hydrogen, 12 atoms, times an atomic weight of 1.0, that gives us 12. Phosphorus, 1 atom times 31.0 gives us 31.0. Oxygen, 4 atoms times an atomic weight of 16.0 gives us 64.0. We add all of those numbers together and we arrive at the molar mass for ammonium phosphate, 149.0 grams for every mole. Ooh. So that means that every roughly 150 grams of ammonium phosphate, I have a mole of it. So if I were to have, let's say, 300 grams of ammonium phosphate, that's 2 moles. If I were to have 450 grams, that'd be about 3 moles. If I have something in between 2 moles and 3 moles, let's say 275 grams, or rather 325 grams, I could calculate the number of grams or the number of moles by dividing the 325 grams by 149 grams per mole, and I'd arrive at something a little more than 2. Good luck with the homework, students.